Humans are gifted at sensing where our body parts are located in space and how they are moving. Interestingly, this aspect of the human experience is poorly understood and often underappreciated. For example, the ease with which unimpaired humans accomplish activities of daily living, as well as extreme athletic performance, is a reminder of the precise sensing and control we have of our limbs. Ongoing prosthetic development projects seek to create artificial limbs that can emulate human motor and sensing capabilities. The work presented here focuses on sensing. A survey of more than 1,500 upper limb prosthesis users found that a major desire for artificial limbs is that they required less visual attention to perform certain functions. We believe that by relaying an artificial limb's position and motion information through a non-visual modality, we can minimize the effort prosthesis users expend on site, as well as enable movements that are less jerky, individuated, and robotic. The objective of this study was to quantify the role visual and proprioceptive motion cues play in a discrimination task to better understand the role of vision and proprioception in upper limb prosthesis use. We designed an impedance-controlled testing apparatus that allows able-bodied users to manipulate an analog to an ideally responsive and controllable prosthesis. The apparatus enables comparison of artificial and real limb use in a spring discrimination task with and without sight. We asked participants to perform a two-alternative forced choice task in which they explored two virtual springs and indicated which was stiffer. Subjects performed this task 150 times for each of three sensory conditions: visual and proprioceptive motion only, and visual motion only. A user of our testing apparatus perceives the location of her right index finger by combining corollary discharge cues, cutaneous force and torque cues at the right index finger, and position and motion cues. The sensory conditions tested differ in the method by which the position and motion cues are relayed. A user of a myoelectric prosthetic arm perceived the location of her artificial limb by combining corollary discharge cues, cutaneous force and torque cues at the socket, the location where the prosthesis is attached to the residual limb, and position and motion cues via sight. In the visual and proprioceptive motion condition, the person visually sees a virtual finger rotating on a computer screen and proprioceptively feels her real finger moving in an identical manner. This condition is analogous to normal human sensing. In the proprioceptive motion condition, the person proprioceptively senses the real finger moving, yet visually perceives no motion information since the virtual finger is not displayed on the computer screen. This condition is analogous to real limb use in which sight is not available, such as when the lights are turned off in a room. In the visual motion condition, the person visually sees the virtual finger rotating on a computer screen, yet proprioceptively does not sense her real finger moving. This condition is analogous to prosthesis use, in which the user's effort controls the motion of the artificial limb, and the limb's location in space is relayed by sight only. Our results are summarized as follows. We found that discrimination performance is comparable in the visual motion and proprioceptive motion conditions, and that the combination of the two does not give significantly different performance. This implies that if we could replace visual motion cues with proprioceptive motion cues, we could minimize the energy expended on vision during prosthesis use. Additionally, we learned that for our setup, subjects perceive proprioceptive motion cues to be significantly more useful than visual motion cues. This implies that users of artificial limbs may prefer having position and motion information relayed haptically rather than visually. These findings indicate that for future work, if we can create reliable artificial proprioceptive displays, we could minimize the effort artificial limb users expend on vision so that the prosthesis experience will be less visually taxing and more intuitive. We would like to acknowledge the listed supporters of this work: